In this lecture, we will deal with mutual inductance, and stored energy. These concepts are fundamental in understanding how magnets interact with magnetic fields and how they store energy. Let's begin by understanding magnetic flux, denoted by phi. Magnetic flux represents the total magnetic field passing through a given area. This is similar to aiming an arrow through a target. The area the magnetic field penetrates is our target. Assume there is a permanent magnet with flux lines each denoted by 0. When the given area is far away from the magnet, its magnetic flux is nearly 0. When the area moves closer to the magnetic flux becomes larger. Here, we can define magnetic flux as the dot product of the magnetic flux density and the area through which the flux penetrates. The unit is Weber. Let's move on to self-inductance. Self-inductance measures how a coil reacts electromagnetically to the magnetic flux it generates by itself. It's a property that quantifies the coil's opposition to changes in current. It is defined as the number of turns of the coil multiplied by the magnetic flux density divided by the current. The unit is Henry. Now, let's discuss mutual inductance. This parameter measures how much a coil reacts to the magnetic flux produced by another nearby coil. This interaction is crucial in systems where energy transfer between different components through magnetic fields is needed, such as transformers. It is defined as shown in the equation, and it is mathematically symmetric. This means the value of the mutual inductance will remain the same even if you exchange the positions of 1 and 2. According to Lenz's law, a coil will resist changes in magnetic flux through it. This resistance is similar to how a resistor opposes current flow, causing a voltage drop. In the case of a coil, it opposes changes in current by inducing a voltage against it. This behavior is fundamental to the operation of inductors in electrical circuits. Magnetic energy is stored in the coil as a magnetic field. The amount of energy stored can be calculated using the coil's inductance and the current flowing through it. This stored energy is a key factor in designing superconducting magnets, as it affects their efficiency and power. Understanding stored magnetic energy is also crucial from an economic perspective. The cost of constructing an LTS magnet is generally proportional to the energy it stores. This relationship helps guide the financial decisions in magnet design, particularly in high-stakes applications like medical imaging and scientific research facilities. To recap, today we explored the concepts of self-inductance and mutual inductance, both of which are essential for understanding how superconductors interact with magnetic fields. We also looked at how superconductors store energy and the relation of this storage with the construction cost.